And now I would like to welcome to the stage Henry de Valence from Penumbra. Bravo.
Hello everyone. So my name is Henry. I'm the founder of Penumbra Labs, who are incubating Penumbra. And today I'm going to be talking to you about some of the aspects of the state model that I think are kind of cool and interesting. Oh, no, there we go. I'm just bad at the remote. All right, so to start off, the useful question is sort of like, okay, what is Penumbra? And I think a good way to conceptualize that is that it's an answer to this question of how do we provide useful functionality on a private ledger? So for the people who have kind of self-selected for a privacy in Cosmos event, I think the value of like having a private chain is pretty clear, at least to this audience. But we have this kind of unfortunate situation in which, on the one hand, we have a lot of people who get a lot of use out of blockchains, and then we also have some private blockchains. And the Venn diagram between those two things, you know, as someone who works on privacy, is like uncomfortably close to two circles, right? So how do we how do we actually build something that is useful? And our answer is Penumbra. So Penumbra is sort of a combination of three things. First of all, we have this private proof-of-stake L1 built on Tendermint that acts as just like a private base layer for everything, has a private staking system, which has some interesting things that we won't be getting into in this talk, but you might want to check out later. And this L1 acts as a cross-chain shielded pool that lets you take any asset from any IBC-compatible chain and shield that asset and record it privately on this zone. Why would you want to do that? It's because we've also built, or by the time this launches, we'll have built this private DEX that allows people to do on-chain trading in a private way. And I think that's actually a really interesting application because trading is a use case where privacy doesn't just have this kind of abstract sort of principled value, right? You know, I believe in privacy, but that doesn't itself make a compelling product. Whereas with trading, you have a situation in which privacy actually has this kind of concrete, quantifiable, near-term financial value that's giving people a positive reason to use this. Okay, so maybe that sounds cool, but there's this issue. Oh, sorry. And this is the diagram of basically how that fits together, right? So you've got this big, beautiful ecosystem in Cosmos at the moment. Everything is transparent. And although there are, not just Penumbra, but other projects that are trying to build private parts of this ecosystem, it does seem pretty clear that we're not going to, just tomorrow wake up and everything is going to be private, right? So from anywhere in this ecosystem, you should be able to do an IBC transfer into Penumbra. And when you do that transfer, you shield your assets, whatever they might be. And then inside of this shielded zone, you can transact, stake, swap, market make, and all the time just have privacy by default. So this is all cool, but okay, like how do you actually build this, right? How do you go from like what would be useful to how are we going to build the useful functionality? And what I'm hoping to convince you of in this talk is that actually the biggest challenge to building a useful private system is not actually the kind of ZK cryptography or like what proof system you're using or whatever, but it's the fundamental state model. And that this is really the big blocker to building useful private systems. So as a bit of context, right? In a traditional blockchain, you have essentially like global mutable state, right? You have, here's the chain state, we get some transactions, I have a transaction, I execute it, now I have a new state, now I'll have this other transaction, execute that one, new state, and I just keep doing this. In practice, it would be kind of annoying to have to come to consensus on every single transaction separately, right? So you bundle them into blocks, but fundamentally, it's a big ball of state, and you change it. And on the other hand, if you have a shielded blockchain, you need to have a different state model that's built on composable state. So this is actually kind of more similar to the original UTXO model in Bitcoin, where instead of saying like, oh, well, we have this like big ball of global state, and a transaction can just like edit that and do whatever, we have this collection of state fragments. And these state fragments are immutable, but they're also composable. So when I have a transaction, what's actually happening is my transaction is going to say, okay, we take these state fragments, we consume them together, we're going to compose them into this new set of state fragments, and then we'll append those into this like big collection of like little bits of state. And why would you need this for building a shielded chain? It's because this is what's going to let you make the whole thing private. And the way that we're going to do that is we replace the actual state fragments themselves with just cryptographic commitments to those fragments. And instead of having, okay, here's the transaction that you can like literally apply, that transaction is going to have just a proof of correctness that these are commitments to the new state fragments that were made according to the rules and stuff. So this is all really cool and awesome and great. And so we've solved the problem. We have all these shielded blockchains, right? No. The unfortunate problem with this is that this only works when there's no shared state, right? And the problem is that whoever is making this transaction has to build this zero-knowledge proof of a complete valid state transition. And so there's two obstacles there. The first is that whoever is making that proof has to have, it's a proof of knowledge, so they have to have knowledge of what the state transition is. So there's no way that I can interact with your private state, right, without knowing what that state is. And also, there's this kind of early binding property, where the transaction has to be this totally sealed blob that completely defines, here's what the state transition is, and you can go execute it. And that's kind of a problem if you're ever trying to interact with some shared resource, because how do you know, right? If you want to submit a swap, right, you can't know in advance, like at the point that your transaction is processed, exactly what clearing price you're going to get in order to be able to kind of pre-seal that into a proof. And so if we return to our question of like, how do we build useful functionality, when we think about what kind of functionality people like to use, essentially all of it involves having some kind of public shared state. And so we can reframe this question as like, how do we allow private interaction with some public shared state? And this, the way that I think about this problem is that this is sort of the problem of shielding value flows. Okay? So what do we mean by that? We have this kind of general situation where there's a blockchain, it has some state, it's doing some stuff, right? And so there's value that's occupying different roles within that protocol, that application or whatever, and there's transactions that are happening, and those transactions are causing value to flow between different parts of this system, right? And the challenge that we have is like, how do we hide information about these individual transactions so it's not possible to see what each one specifically is doing, while still revealing information about the kind of overall aggregate state of different parts of this system. So as an example, right, how do you hide the amounts of each person's delegation, but still be able to see the kind of aggregate total voting power of all the different validators? Or how do you hide individual votes, right? I mean, you definitely want to have private voting because otherwise people are just going to like airdrop bribes to people. But you still need to be able to like figure out what the governance outcome is. The motivating case actually for Penumbra was like, how do we hide individual trade amounts but still reveal the reserves of the AMM? So there's a kind of cute paper by Tarun and Guillermo and Alex about how, like if you have the AMM before the trade and after the trade, like it turns out you can just like, plug in a formula and figure out exactly what the trade amount was. And then the last one that I think is kind of, topical here is like, how do you hide bridge transfers while still revealing the chain solvency? So these are all actually kind of like different facets of the same basic problem. And there's sort of two fundamental kind of classes of strategy for dealing this that go in opposite directions. So the first one is trying to split up flows into little chunks. And then the other thing you could do is you could batch flows into bigger chunks. What does that look like? So in the first case, right, splitting, you could imagine some user has some like amount, and they're just going to split that into some randomized sub-amounts. Maybe they have some user agent that will do this for them. And then they'll like spread those out into some like different transactions that each has like a little part. And then later they'll try and like reassemble them and just like hope that whoever's looking at the chain doesn't know statistics. So that's like obviously kind of suboptimal. But I would say that the one thing that is good about this is if you do end up in this kind of happy world where there's like multiple private chains, there is some sense in which this isn't necessarily the worst thing. Like if you tried to do this on a transparent chain, you're gonna like definitely lose right away. But there's a kind of like worse is better thing in that this is like something that some individual user can do on their own without requiring any kind of protocol changes or whatever. But definitely not the thing that you want to build, like your whole protocol on. And so the second kind of class and alternative is batching flows. So here, instead of having just one user, let's say we have a bunch of these different users with different values, and what they're going to do is they're going to encrypt all of these integer amounts using a primitive that we've started calling flow encryption. So you can think of this as basically like a sort of spicy additive homomorphic encryption. And the reason to pick a different name for it is that once you start thinking about how do we integrate this into a blockchain, you come up with this like long list of like all these extra properties that it has to have in order for it to actually like function as part of a system. And at that point, it's better to have a distinct name for the concept. So we have some docs on this on our protocol spec, but effectively the flow is that once you have these ciphertexts, right, they're all additively homomorphic, so the chain can aggregate all of the encrypted values over some interval. Maybe that's over a block, maybe that's over a full day, maybe longer or shorter. It depends on the application logic and the context. But then the validators can do threshold decryption to reveal only the batch total for that whole amount. And once they have that batch total, they can use that to do some public on-chain computation. And at that point, okay, it's like, this is cool, but how do we actually use this? So if we return to this original problem that we had of how do we allow private interaction with public shared state, this mechanism of using flow encryption to do batching actually lets us do this in a way that is pretty cool, but has some interesting consequences for the state model. So we'll start off with some user who has some private input. And what they're going to do is create some transaction that does something. What it is might depend on the application, but that transaction is going to have, along with whatever else, some encryption of their input, which is their contribution to some part of the flow, of some kind of flow. Whether that's their vote, whether that's an input to a swap, whatever. And they make that transaction, they submit it to the chain, And the other side effect of that transaction is that they're going to get this kind of private state NFT. It acts as basically like a receipt for participation. So what happens when that transaction is actually processed and included in the chain? It gets batched together with some other inputs from some other transactions. Maybe this, will take some time if there's like a very long batch interval, depending on the application. But at some point, the validators will aggregate that together and then decrypt some batch total. And at that point, right, they're going to do this public computation. And the neat thing is that then you can have public outputs of that computation that get committed to the chain state. And at that point, the user who originally submitted their this transaction can use their private state NFT to effectively just like mint some new private outputs. And as part of the transition proof for their outputs, they can use the results of this public computation. So for instance, if you wanted to do a shielded swap, right, your input is like, the amount that you're submitting to as part of the trade, and the public computation is like, okay, well, we'll go and like resolve all these like batches of trades. Maybe we'll do arbitrage and consensus or some other, sick hacks, and then end up with all these clearing prices, and now everybody can just like mint their new tokens. And so this is a kind of really interesting model because it's dealing with the problem of having interaction with shared state by basically explicitly segmenting the activity into distinct phases where someone is submitting part of an entry into a batch, and then later using the results of the batch computation to prepare their outputs. And as a side effect, you end up with having the chain basically execute every piece of functionality, whether that's explicitly kind of as a smart contract or part of the consensus. But effectively, every contract instead is just going to execute once per block, so you can get some considerable efficiency savings. And you end up getting a kind of neat property, which is that you have no transaction ordering because everything is just batched together anyway. So once a transaction is included in a block, the ordering within that block has no effect on the results of the execution. And there's also no visibility into what the transaction does prior to it being processed. And so if you think of what's going on with MEV, you're basically saying, okay, some like block proposer is going to get some like actionable information about the transaction and use that to discriminate against it. But first of all, it's not actionable because there's no transaction ordering, and second, there's no information because there's no transaction visibility. And so the result is that by design you have like effectively no MEV. So yeah, anyway, that's the punchline. I think this is a kind of neat model for how to go forward, and happy to have any questions.
Yeah, very cool project. I had a question. So if there's no transaction ordering and everything is sort of batched together, what kind of impact do you expect it to have on like pricing in AMMs for the end user?
Yeah, so there's definitely trade-offs with this approach. One is that you are kind of, well, okay, so I'll separate two things. First is like there's the concept of just like having this type of state model, and then there's also what we're going to be doing with Penumbra specifically. So in general, with this class of state model, you could still have that type of control. So for instance, you could say every input is going to set its own custom slippage limit or something, and as part of this like batch processing, you would like sort them all by slippage limit, and then the ones that were above would just not be processed. And so I don't think that there's any inherent kind of issue with this type of like just fully commit to batch processing of everything and not having transaction ordering. For Penumbra specifically, we want to achieve long-term privacy for individual trades, right? So unlike a system where it's like, okay, well, we'll encrypt transactions until they're committed, and then we'll disclose them, right? We want to have them be protected also after they're executed. And so we basically, in the AMM design, we sort of pick two different trade-off points on privacy versus fine-grained control over trade execution. And on the market taker side, we prioritize privacy. But on the market maker side, we prioritize the execution control. So all of the AMM positions are public but anonymous. And so the idea is like, okay, if you would really like to have like really exact control over your execution, then you might want to use like a concentrated liquidity position as a limit order. Or alternatively, if you're want to like stay on the market taker side, you could do something like sharding your execution into like multiple sub transactions that you spread out over multiple blocks, so that you're minimizing the sort of price risk of ending up in a batch with some whale or something.
I have a question. So thanks a lot for the talk. So in this particular model, what happens if one of the individual transactions that were batched, what happens if this transaction is actually invalid? And does that open some room for denial of service attacks?
So the really cool thing about building the chain around ZK proofs is that you can guarantee that that isn't the case, right? Because before you batch the before you take some transaction and include it into the batch, that transaction has to have a whole complete set of validity proofs that establish that it is an allowable state transition. And so at the point that the chain is aggregating these contributions, it can already be assured that they are definitely guaranteed to be correct. But that is actually a big issue, and it's one of the sort of finer points of like what is like this concept of flow encryption. One of the additional properties that you end up needing that's beyond just like additively homomorphic threshold encryption is you need to have a strong kind of end-to-end verifiability that like all of the ciphertexts were well-formed, and that all of the aggregation was done correctly, and that none of the validators like substituted a different decryption, and have this kind of end-to-end integrity of the value flow through the whole system.
Cool, thanks. Should I just throw? But it's very far.
Hey, thanks for talk. I was talking to Lido at one point about encrypted mem pools, and they raised an interesting concern, which was basically like opening up spam vectors. So in this case, you have no ordering within the block or like the segment that you're anonymizing, but one could potentially just flood the mempool with like microtransactions to like eat up the entire segment, and then just have like one large trade in that period. So do you have like mitigations for this kind of attack? I mean, their thesis is like MEV just like cannot be eliminated. It can only be like pushed into other kind of domains, which I thought was like an interesting perspective.
So I think it's kind of important to note that we don't actually have like an encrypted mempool, right? It's that all of the transactions that are in the mempool don't reveal any information. And so at that point, you don't have a particular concern about, at least if I'm understanding the question correctly, I don't think that you have a particular concern about denial of service attacks that is any different from just like being able to DOS a chain by submitting a bunch of like spam transactions, right? Like all of these transactions are going to have to pay a fee. And the nice thing about batching is that if somebody is like adding a bunch of extra transactions, like that's just increasing your own privacy.
Interesting.
So if you're using a zero-knowledge proofs for all this, are you only charging a fee, or do you have any sort of gas as well for this?
So we're still kind of like refining exactly what the cost model is going to be like, but there are fees, and what we're probably going to end up doing is having a kind of like lightweight, like So one thing I guess that is a difference is that when you have a shielded transaction with these sort of pre-finalized, like sealed state updates, on the server side, to validate that, you're not having to do like execution. And so you can just like know exactly what the cost is up front. And so we're probably going to end up with a fee model where, you know, if you add, like if your transaction is bigger and it does more expensive stuff, it has more proofs in it, like your required fee will probably end up being higher to like account for that cost. But a lot of the complex resource use problems that come from having this like on-chain execution actually go away in a shielded model because the actual state transitions are happening off-chain. And what we're left with is, so just to rewind to this kind of batch processing diagram, another thing that's very cool about only executing each piece of functionality once per block is that you get to amortize the cost of that execution over every single transaction. And so depending on which way you go, right, either that could be much cheaper, or you could say for the same amount of cost, we could do like much more like computationally intensive processing and do cooler things as part of the app logic.
Thank you very much. Thank you, Henry.
All right.